In this video, we're going to look at electron configurations. So Niels Bohr talked about electrons existing in these energy levels or shells or rings outside the nucleus. And we're going to connect that to the periodic table here and then try to see how electron configurations can show those, really those electrons in those shells or those rings. So if I look here at a periodic table, I'll notice there's 1, 2, 3, 4, 5, 6, 7 rows. Let's be careful with these last two because where do these fit in? The sixth row, cesium, barium, and then lanthanum, cerium, and so on would go right in there. And then the seventh row, francium, radium, actinide, and so on would be fitting up in here. So let's take a look. We got 1, 2, 3, 4, 5, 6, 7 rows, which really corresponds to 7 shells of where electrons could be. There's technically more of an unlimited number of shells where electrons can go to, but they would only go to those higher energy spots if they got a current plugged into them and the electrons got excited to a higher level. Usually they're going to be in their ground state, which will be in these lower levels right here, and that's what we're going to be studying and really coding so we know where these electrons are within these shells and even subshells. So let's look at the first thing. The first shell has room for 2 electrons. Notice these noble gases here are the point where shells get completely filled. So when you get to helium, you have filled the first shell. The next, down here, when 2 shells are completely filled, there's 10 electrons. 2 in the first shell, 8 in the next shell, for a total of 10. The next shell, the third one, has room for 8 electrons as well. So 2 plus 8 plus 8 would equal 18, and we're at argon. The fourth shell has room for 18 electrons. Okay, so 2 plus 8 plus 8 plus 18 is going to be 36. The next shell also has room for 18 electrons, and we have 36 plus 18 gets me to 54. The sixth shell has room for 32 electrons. Going from 54 to 86 is room for 32. Remember, we start here and we include these 14 down here to go with these 18 over here to be 32 in the sixth shell. And the seventh shell also has room for 32 electrons. So you can see these shells, 2, 8, 8, 18, 18, and then a maximum of what, 32 and 32. Okay, if all the shells are filled, we're at element 118 right here. Let's look at a little different diagram that shows this. And this is, okay, here we go. This is an off-baud diagram chart, and it's like the same thing, but it starts at the bottom. There are room for 2 electrons in this first shell, and then there's a gap, and then there's room for 8 electrons in the next shell, then there's room for 8 electrons in the next shell, and then there's room for 18 in the next shell, and so on. So it's like what I was showing you the periodic table, except it goes bottom to top. And there's a reason for that. I think we're going to show this as we scroll up here. So what we're going to do is kind of use this chart as a guide to figuring out where electrons go in these shells and even in subshells. So the first rule is the off-ball principle, and it says electrons enter orbitals of lowest energy first. And that's why we're starting bottom to top. At the bottom is the lowest energy, or the 1s level, which would also be at the top of the periodic table. So that's where we're going to start out at. A lot of things in nature try to go to the lowest energy, thing. It just automatically goes that way. And these electrons are certainly will follow that principle. The next thing is something called the Pauli exclusion principle, and it just says an atomic orbital can contain a maximum of 2 electrons. So first off, what is an orbital? An orbital is a place where electrons are likely to be found. We talk about shells or rings or energy levels, but because we don't see electrons, we still like to talk about them in terms more of probability. Instead of just saying they're here, they're likely to be here. Okay, each orbital has a room for 2 electrons. Okay, so there'd be a maximum there, since an orbital is like a box. So this box means there could be 2 electrons. There's 1, 2, 3, 4 boxes, so there could be 4 times 2 or 8 electrons here. 4 boxes or 8 electrons here. 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes, so there could be 18 electrons here. That would be the maximum capacity. Okay, I'm just going to go back up here a second to these rules, and it says an atomic orbital can contain a maximum of 2 electrons. I'm going to go to the next rule. When electrons enter orbitals of equal energy, 1 electron enters each orbital until all the orbitals contain 1 electron with parallel spins. Only then do the electrons begin to pair up in their orbitals. So we'll get more back to this Hund's rule because that seems pretty confusing, but there's this idea of electron spin, and I think we should talk about it real quickly here. So electrons are going to repel. I'm going to go away from the screen here for a second. Just look here. They're both negative, so they're going to repel each other. However, they spin around, they're mini spheres, and just like the Earth spins around and it's a sphere, it has like a magnetic north pole and a magnetic south pole. These electrons also have a magnetic north and magnetic south. So if the electrons are lined up where like poles, kind of like the light colors here, I don't know if you can see the red or the black, but here the 2 blacks are on top, the 2 reds are on the bottom. They're going to repel each other more than expected because not only electrons are repelling, but the poles are repelling. Let's say I just flip one of these around, and now the 2 electrons are still going to repel, but they're going to repel a little bit less than expected because the opposite poles are now across from each other. So what do electrons do? They stop and spin one way or another way. No, they automatically flip around to go to the most stable spot. Just like birds flying south automatically fall in line of an echelon to save energy while fighting the winds. So things will go to the most stable spot, and we're going to represent that with an up and down arrow when we draw our electron configurations. All right, we should probably get to drawing 1 or 2 of these and right here. Okay, so what I'm going to do is say, oh, we want to fill in electrons. I'm going to go and do this for hydrogen. Hydrogen has 1 electron. It's going to go to the lowest spot. It's going to go to the 1s level. I'm just going to draw an arrow and kind of an up arrow. I usually just do half an arrow for convenience. And if I wanted to write what this was, I would say hydrogen like this. And then I would say 1s1, meaning there's 1 electron in the 1s level. Now let's say I've had 2 electron atom like helium. Is there still room in the 1s level? The lowest level here is still open, and you could have a maximum of 2 electrons. So there's other electrons like, I could go out of my room, but I don't want to climb these stairs up to the next thing. I'm tired. I've been at an electron convention, a lot of negativity surrounding me. So I'm just going to go down here, but I am going to spin the opposite way. And if we were talking about an electron configuration for a 2 electron thing, which would be helium, we would say helium would be 1s2, because there are 2 electrons in the 1s level. Let's say we decided to go to lithium, and I am going to put, oh, there's no room in the 1s. I'm going to go to 2s, and I'm going to put an electron here. Just I arbitrarily always do the up arrow first and the down arrow last. It's really arbitrary, but that's what I would do. If I were writing the electron configuration for lithium, okay, that's lithium, I'm not going to dot the I. It's going to be 1s2, and then it's going to be 2s1, meaning there's 1 electron in the 2s level and 2 electrons in the 1s level. And we can keep building this from here, but I think I'm going to stop this video here, and then we'll continue with this from there. But these are electron configurations, and we'll keep building some of these and then connect it again back to the periodic table. Thank you.